Welcome to the debate. When we look at the modern industrial world, the massive engines, automated factories, the robotics, we tend to think of it as this sudden explosion of light.
Right, like a switch just flipped in the 18th century.
Exactly. Suddenly we had machines doing the heavy lifting of civilization. We picture figures like James Watt striking a match in a completely dark room. But when you actually step back and peer into the shadows of antiquity, the room wasn't dark at all.
No, there were sparks everywhere.
Yeah, gears turning, water lifting, steam hissing, complex mechanisms operating centuries before the Industrial Revolution even had a name. So today is a Decoding Pillars of History special discussion for us. We are opening up an analysis of the Chronicle of Ancient and Medieval Genius, and we're focusing specifically on the ambitious goal of curating a master collection of pioneers and inventions.
Which is a huge undertaking.
It really is. We are going to be looking closely at the ancient archive blueprints that laid the actual foundations of our modern world. And our central question is this: between the ancient theoretical breakthroughs of Hero of Alexandria and the sophisticated medieval mechanical developments of Ismail al Jazari, who had the more profound impact on the trajectory of modern engineering?
A massive question.
Right. So I will argue that al Jazari's translation of raw invention into documented practical machinery makes him the true father of modern engineering.
And I will counter that Hero of Alexandria's conceptual mastery of pneumatics and, invisible forces established the foundational physics without which later engineering would be utterly impossible.
Okay, to start us off, I think we have to define what it actually means to catalog human ingenuity. If we are building a true master collection, we must prioritize practical application.
Sure, utility matters.
It's everything. Al Jazari's 1206 text, the Book of Knowledge of Ingenious Mechanical Devices, it was not just a collection of abstract theories or philosophical musings. It was essentially a practical do-it-yourself manual designed specifically for human comfort and utility.
A very complex manual, but yes.
Right. And he introduced concepts that are absolutely critical to what would become the Industrial Revolution. We are talking about the camshaft, the early crankshaft, and really the first true documented conversion of continuous rotary motion into linear reciprocating motion.
Which is a big deal mechanically.
It's a huge deal. His work laid the direct, undeniable groundwork for modern robotics and the combination of mechanical linkages that would, eventually allow the steam engine to do actual labor.
Look, I hear that, and I deeply respect the mechanical genius of al Jazari. But I have to argue that the highest form of genius is found in conceptual breakthroughs that completely shatter contemporary paradigms.
Okay, but shattering paradigms doesn't mill grain.
Well, let me finish. Hero of Alexandria, who's building on the work of predecessors like Straton and Philon back in the 1st century, he did something far more profound than arranging gears. He manipulated invisible elements.
You mean the steam and air?
Exactly. He worked with atmospheric pressure, vacuums, and steam. His pneumatic devices are, they're frequently dismissed by historians as mere toys or parlor tricks, but they were actually highly rigorous scientific experiments.
Rigorous might be a stretch for some of them.
No, really, take his steam engine, the aeolipile, or autokinetic sphere. This was a deliberate philosophical counterexample to Aristotle's prevailing theory of motion. Aristotle had the entire ancient world convinced that movement could only occur if an object pushed against an external supporting medium.
Right, the unmoved mover concept.
Yes, and Hero proved that movement could occur in a self-contained system without that external pushing. Without this massive theoretical leap in pure physics, the practical engineering you're talking about eventually hits a wall.
I see why you think that, but let me give you a different perspective on aeolipile, because I think sticking the steam engine label on it gives him far too much modern credit.
Oh, come on, it literally runs on steam.
Sure, but if we are evaluating these ancient archive blueprints, we have to evaluate utility and mechanical viability. Hero's aeolipile was incredibly inefficient. Mechanically, it was just a hollow sphere mounted on an axis, propelled by steam shooting out of two bent opposing nozzles.
Right, a pure demonstration of force.
But here is a critical flaw. It had absolutely no simple reduction gearing to transmit that power. It spun wildly fast. We estimate over 1,000 revolutions per minute. which means it spun too fast to be connected to any useful load without tearing itself apart.
Well,
And furthermore, the mechanics of it were terrible. It suffered from extreme friction and massive steam leakage at the rotating sleeve joint, what the Greeks called the smerisma. It could not do work. It didn't lift water, it didn't grind grain, it didn't move earth. It was a philosophical statement on a table, not a tool for human progress.
I come at it from a different way. You are entirely correct about its mechanical inefficiency. The leakage at the joint was indeed a major energy loss. But, you are judging a first-century scientific instrument by the standards of an 18th century textile mill.
Because we're talking about the impact on modern engineering.
Yes, but the inefficiency is moot because the idea is what matters. Think about what the aeolipile actually did. It demonstrated Newton's third law of motion, jet propulsion, the concept of equal and opposite recoil, more than 15 centuries before Isaac Newton formalized it.
I'll grant you the physics demonstration.
right. As I mentioned, Aristotle argued that a moving object must push against something unmoved and external to it. Hero created a device that generated its own recoil entirely through expelled gas. He proved that the abstract laws of physics could be isolated and harnessed. That conceptual leap is exactly what shifting human understanding of natural laws is all about.
That's an interesting point, though I would definitely frame it differently. Shifting conceptual understanding is wonderful, but engineering, by definition, is the application of physics to solve human problems.
And understanding the physics is step one.
But if it doesn't solve a problem, it's natural philosophy, not engineering. Look, let's make this concrete. If we were trying to explain the foundations of our discipline to a first-year engineering student today, and we had to pull just one blueprint from our respective inventors to show them what true engineering looks like, I would point straight to Al Jazari's twin-cylinder pump.
Oh, I love that you brought up the pump because it sets up the perfect contrast with Hero's work. Walk me through exactly how you would present those mechanics.
Okay, so if I'm unrolling the schematic of Al Jazari's Bible action suction pump for a student, I'm showing them a machine that solves a massive fundamental problem, taking the continuous rotary motion of a water wheel, which just spins endlessly in a river, and converting it into linear back-and-forth reciprocating motion.
The holy grail of mechanical engineering.
Exactly. I would trace the mechanics step by step. The water wheel turns a system of gears. Those gears drive an oscillating slot rod. Now, this slot rod is the brilliant part.
Right, because of how it connects.
Yeah, it's attached to two pistons operating in horizontally opposed cylinders. As the gear turns, it pushes the rod back and forth, driving the pistons in alternating strokes.
It's conceptually the inverse of a modern internal combustion car engine.
Precisely. In a car, the linear motion of the pistons turns the crankshaft. Here, the rotary motion of the wheel drives the linear motion of the pistons, but I would really emphasize how it pulls the water.
The valve system.
Yes, each cylinder has a valve-operated suction pipes. As the piston pulls back, it increases the volume inside the cylinder, which drops the pressure. It creates a partial vacuum. The atmospheric pressure outside the machine then forces the river water up through the valve and into the pipe.
Right.
Then, on the return stroke, the intake valve shuts and the piston forces the water out through delivery pipes. And Al Jazari engineered these delivery pipes to join at the center of the machine into a single continuous output. It is a masterpiece. And, he achieved a watertight fit in 1206 AD without modern machine tools by using emery powder.
Wait, the abrasive compound?
Yes. He used emery powder to meticulously grind the copper metals against each other until the clearance was so incredibly tight that no water could escape the cylinder. He essentially invented precision machining. He didn't just have a theory about vacuums. He built a tightly sealed, statically balanced machine to exploit them for continuous labor.
Okay, it is a beautiful machine, and the use of emery powder for precision grinding is a phenomenal technical achievement. I will grant you that. But if I am standing in front of that same engineering student, I am going to put away the heavy gears and pull out Harrow's squirt, which is detailed in his treatise Pneumatica, section 1.10.
Oh, this is the device that was essentially used for putting out fires?
Yes, or spraying perfume, depending on the scale.
I would tell the student that they are looking at the direct conceptual ancestor to modern aerosol cans, medical syringes, and internal combustion fuel injectors.
That's a big claim for a simple pump.
The mechanics are elegantly simple, but the physical principles are profound. We have a piston pump that physically forces air into a spherical vessel. And I would ask the student right there, why did Hiro choose a sphere?
Because of stress distribution, obviously?
Exactly. A structural engineering lesson nested in a pneumatics lesson. A sphere is mathematically the optimal shape to withstand internal pressure because there are no corners or sharp edges where mechanical stress can concentrate. Hiro intuited this.
Fair enough.
Then I would look at his version of the smerisma, the watertight ground joint or stopcock. As the piston forces more and more air into this sphere, the pressure builds enormously because air is highly compressible. Water, however, is not.
Right.
So when Hiro's adjustable outlet valve is suddenly opened, the compressed air forcefully expands to its normal volume, acting like a physical spring that violently ejects the water out of the nozzle. Through this single blueprint, you are teaching a student the compressibility of gases, the incompressibility of liquids, and the fundamental laws of hydrostatics. I mean, al Jazari gives them the gears to move the machine, but Hiro gives them the invisible thermodynamics that power the modern world.
Okay, I'm not entirely convinced by that line of reasoning because you're treating water strictly as a passive element to be pushed around by air acting as a spring. If we really want to evaluate their engineering genius, let's compare how both of these men actually mastered water power.
I'm happy to do that.
Because water was the defining power source of both of their eras. But they manipulated it differently. Al Jazari used water for incredibly complex mechanical switching, logic gates, and automation. Take his peacock fountain, which was designed specifically for the ritual washing before prayer, or wudu.
Oh, the fountain that featured the humanoid automata?
Yes. And it wasn't just the fountain, it was a mechanically programmed robot. The user comes up to it and pulls a plug on the peacock's tail, which releases a measured flow of water. Now, here is where the genius lies in the how. As the dirty water from the user's wash basin drains, it doesn't just fall away, it intentionally fills a hidden hollow base inside the machine.
Right.
Inside this base is a float. As the water level rises, the float rises with it, utilizing buoyancy as a physical driving force. This rising float pushes a vertical rod, which acts on a hidden fulcrum lever.
So it's essentially a mechanical tripwire.
Exactly. The lever reaches a tipping point and trips a latch. That latch triggers a door to swing open, and a mechanical humanoid servant emerges holding a piece of soap.
That is incredibly theatrical.
It is, but it's brilliant. As the user continues to wash and more water drains into the base, a second float situated at a higher elevation is eventually submerged. It rises, trips a second fulcrum linkage, and a second servant emerges offering a towel. Al Jazari didn't just use water to push a wheel. He used the accumulation of water to track time and actuate sequential mechanical linkages.
Which he also did in his clocks, right?
Yeah, he did the exact same thing in his water clock of the drummers, where slowly draining cisterns would gradually fill tipping buckets. Every hour, a bucket would reach its critical weight, suddenly tip over and release a rush of water over a wheel. That wheel turned a camshaft, and the cams would physically trigger the arms of a robotic musical band to strike their instruments. He used the fluid dynamics of water to create timed, programmable logic.
Look, I'm sorry, but I just don't buy that represents a higher conceptual mastery of the element.
How can you not? It's literally programming with water.
It is brilliant mechanical linkage, yes, but fundamentally, Al Jazari is just using water's weight. He is using its gravity, its mass, and its buoyancy to push levers and turn wheels. He is treating water as a heavy rock that flows. Hiro, on the other hand, used water for phase changes and thermodynamics. He didn't just use water's weight, he fundamentally changed its physical state to extract energy.
You're referring back to boiling it into steam for the aeolipile.
Not just the aeolipile, look at the thermoscope, which Hiro perfected from Philon's earlier designs. The thermoscope was the direct ancestor of the thermometer. It brilliantly demonstrated that changes in temperature could cause water to be drawn into or forced out of a spherical pressure vessel.
Okay, how did that mechanism work exactly?
The mechanism is beautiful in its simplicity. You have a sphere containing air, connected via a tube to an open container of water. When you expose the sphere to heat, even just the ambient heat of the sun, the air molecules inside the sphere gain kinetic energy. They move faster and spread out.
So the air expands?
Yes, the air expands. This invisible expansion creates increased pressure that physically pushes down on the water in the tube, forcing it out.
And when the heat source is removed?
Well, when you cool it down, the air molecules lose kinetic energy. The gas contracts. This creates a partial vacuum inside the sphere, and the heavier atmospheric pressure pushing on the open container of water forces the liquid back up into the tube to fill that void.
So it's measuring temperature via displacement.
Exactly. Hero was mapping the unseen mathematical relationship between heat, pressure, and volume. Al Jazari made water do physical labor by dropping it on things, which, is structurally impressive. But Hero realized that water could be transformed from a visible heavy liquid into an invisible expanding gas that held trapped kinetic energy.
I see the distinction you're making.
That conceptual leap, the understanding that heat could be converted into pressure and motion, is the absolute prerequisite for the steam engines that would eventually drive the very mechanical linkages Al Jazari perfected.
Okay, well, if we are summarizing their ultimate places in the chronicle of ancient and medieval genius, I have to stand firmly by my position. When you catalog historical human ingenuity, it reveals Al Jazari as the absolute pinnacle of practical world-building progress.
Even without the thermodynamics?
Yes. Theoretical daring is a luxury of philosophers. But Al Jazari's legacy is written in the camshafts, the segmental gears, the double-acting pistons, and the robotic linkages that physically constructed the modern industrial age. I mean, he took the theoretical, ground it down with emery powder until it fit perfectly, and made it tangible. He created machines that solved actual human problems without waiting 1,500 years for someone else to figure out the application.
And I will reassert that Hero of Alexandria represents the true genesis of modern engineering. You simply cannot have a modern industrial revolution with just water wheels and gears.
They certainly help, though.
They do, but gears only transfer power. They do not generate it. You need an independent prime mover. You need thermodynamic power. Hero's legacy is the intellectual courage to look at invisible forces, to isolate them, and to prove that the abstract laws of physics could be challenged, manipulated, and bent to human will. He gave us the thermodynamic soul that would eventually inhabit Al Jazari's mechanical body.
Well, perhaps the real takeaway from examining these ancient archives blueprints is that you simply cannot have one without the other.
That's very true.
If you have Hero's mastery of invisible forces and thermodynamics without Al Jazari's precise mechanical linkages and gears, you just have a hissing, spinning toy on a philosopher's table.
And conversely, if you have Al Jazari's brilliant cams and linkages without Hero's understanding of thermodynamics and phase changes, you are forever bound to the speed of the local river. Modern progress genuinely required both halves of the equation, the theoretical daring of the ancient world to unlock the power, and the practical, mechanical brilliance of the medieval world to harness it.
There is clearly so much more to explore in the source material. The evolution of engineering isn't a single clean line drawn from the past to the present. It's a deeply woven tapestry of theory and application.
Indeed. And it leaves us exactly where we started our conversation today.
Staring into that dark room of history.
Realizing it was never truly dark at all. The sparks of genius were always there, just waiting for the right minds to connect the gears to the steam.